What do you suppose feedback excitation looks like? The same thing except for cell 3 is excitatory. Yeah.
One inside cell 3D.
Right now, cell 3 is inhibitory.
Oh, you're talking about the excitation, sorry.
And for feedback excitation, you can either do it as just 2 cells. It still would be feedback excitation if you have 3 cells. But the key is that the activity of cell 1 via this feedback circuit influences the activity of cell 1. Okay? So it's feeding back to that initial neuron, to cell 1.
Can you slow down?
Yeah, all of these are also on the next slide in the PowerPoint, and they're all on Neuroscience Online. Okay, so these microcircuits, we're just drawing individual neurons, right? But in reality, in our nervous system, we have lots of neurons that work together to achieve a goal. In some cases, we have lots of neurons synapsing on one downstream neuron. In other cases, a single neuron synapses on a number of its own downstream neurons. Those circuits are called convergence and divergence. Okay? Convergence, we have a bunch of neurons synapsing on one downstream neuron. And then what do you suppose divergence is?
Multiple.
One onto multiple. And I'm intentionally not drawing this as excitatory or inhibitory because it can be any combination. And in reality, it is many different combinations. A single neuron receives excitatory and inhibitory information all at the same time. And it has to put all of that information together. What is that process called? Neural integration. Right? Did you have a question?
Can you repeat what divergence was
Divergence is one to many.
One neuron on one to many.
One to many versus many to one. Okay? And here are those same figures, but from Neuroscience Online. Slightly prettier, I suppose, than I drew them. And they do also, they don't change the shape of the cell body, but they do have the terminal shaped differently. The excitatory neurons, they have a triangle. The inhibitory neurons, they have a circle. So hopefully that will help so you can decipher.
So the convergence and divergence, is that excitatory?
Here they've drawn it all as excitatory. I drew it as brown rather than red or green because in reality, neurons are receiving lots of different information all at once. Now here, this neuron in the middle, this one is either going to excite or inhibit all of its downstream connections because one neuron can only be excitatory or inhibitory. But this neuron might be receiving excitatory and inhibitory and modulatory information all at the same time. Okay, now we're going to do an exercise where we put a couple of different pieces of information together. We have a new microcircuit. Cell 1 is excitatory. That means it releases glutamate. Cell 2 is inhibitory. It releases GABA. cell 3 is also inhibitory and releases GABA if it fires an action potential. And cell 4 is excitatory, and if it fires an action potential, it would release glutamate. Okay. So here's the question that we're ultimately going to ask. If cell 1 fires action potentials and releases neurotransmitter, what is the final effect on cell 4? Okay? And to answer that question, we're going to take it one step at a time. On your own first, if cell 1 fires action potentials and releases neurotransmitter, what is the effect on cell 2? EPSP, IPSP, no change, or cannot determine based on the information provided. Okay, let's briefly turn to your neighbor, convince them that you are right. If you have the same answer, come up with why that is the correct answer and the other ones are not correct. Most of you did have the correct answer. When you're ready, go ahead and vote again. Yeah, so cell 1 fires an action potential, it releases glutamate. Glutamate causes an EPSP on cell 2. Now let's ignore cell 1 and look at the synapse between cell 2 and cell 3. If cell 2 fires action potentials and releases neurotransmitter, what is the effect on cell 3? Okay, so yeah, all of you have the correct answer. Cell 2 fires action potentials and releases GABA. That will cause an IPSP on the postsynaptic membrane of cell 3. Now let's ignore cell 1 and cell 2 and focus on the synapse between cell 3 and cell 4. If cell 3 fires action potentials and releases neurotransmitter, what effect does cell 3 have on cell 4? Okay, yeah, so cell 3, if it fires action potentials, will release the neurotransmitter GABA or glycine, and that will cause an IPSP on cell 4. Let's draw what that IPSP looks like. What is my x-axis going to be? Time. And my y-axis? Membrane potential in moles. What is rest? Okay, and let's put EK in here just for some context. So this is, we're recording from cell 4. Here cell 4 is bopping around at rest. Cell 3 releases neurotransmitter. What happens to membrane potential on cell 4? What does it look like? Draw it in the air with your hand. Okay, yeah, so we're drawing an IPSP, right? Okay. Now let's go back to the bigger question. Cell 1 fires action potential and releases neurotransmitter. What is the final effect on cell 4? Keep in mind that these things are not happening in a vacuum. All of these have other synapses going on. And think about how membrane potential of cell 4 will change if this whole pathway occurs rather than just cell 3 to cell 4.